I'm Aki Fujimura, CEO of D2S. Today I want to talk to you about pixel level dose correction. Pixel level dose correction, or PLDC, is a type of MPC, but it's very different from conventional MPC. PLDC improves both uniformity and linearity, and it works for any shape equally well, equally accurately, and all of it in zero turnaround time impact. The correction is happening while the mask is being written. I want to show you a series of 3 pictures. First is this Manhattan one. We start with Manhattan because that's really important. One of the benefits, certainly, of PLDC is that it works well for any shape. It's shape agnostic. But that it works really, really well for Manhattan shapes is an important thing because majority of the masks in the world today are Manhattan shapes. What's on the left is the target mask shape. What's on the extreme right is the PLDC corrected SEM result. What's in the middle is an overlap between the two. You want to see the least amount of difference between the 2 shapes. And you see that. Curvilinear shapes, it works very well too. You can see that there is very little deviation between the purple shape and the same picture. Doesn't matter if it's small or big. Now, you can give it shapes that are mask rule incorrect. It will do the best it can. Right? These kinds of shapes where you have pointy ends, they're limited by both the pixel size of the mask writer and resist blur even before anything comes into play with PLDC. PLDC does the best it can to try to get the machine to write as accurately as possible, but if it's mask rule incorrect, there's a limit to what it can do. The question is, though, the behavior of the correction when it's trying the best it can. This target shape has a circular inner thing, right? The ends of the points are supposed to be a circle. If you draw that exact circle on the right side, you get that. It's not quite reaching that, right? The question with PLDC or any MPC applied to this kind of a shape is, okay, it's impossible to reach the middle circle. It's going to be further out than that, but is it further out uniformly across the circle? Is it a bigger diameter circle, or does it become a different shape on the inside as you do a correction? I can tell you this is a challenge, right? And it would be a good test for any MPC that is applied for curvilinear masks. And you can see in the purple the same diameter difference. So what's different about PLDC? I mentioned any mask shape. It's any mask shape because it's PL, pixel level dose correction. It's not working with vertices, it's working with pixel doses. It's a fundamental computing difference in how it works, in a similar way to how multi-beam mask writer writes differently from how BSB wrote the masks. So it doesn't matter what shape you got. PLDC would correct the shape equally well and in the same amount of time. PLDC also improves both linearity and uniformity. I'll explain the uniformity picture that's on the right here in a second. Linearity includes both dose-based effects and variable bias effects, and I'll explain that in a little bit too. PLDC works on any masks, including 193i, or for that matter, 193Gi, or EUV or high-NA. Particularly as we go to EUV and high-NA, it becomes important that PLDC inherently corrects the full reticle for all chips in their local context. That's really important because in EUV, for example, in the X direction, because of the through-slit effect, the correct OPC or correct IoT will not have the same mask shape across the X dimension, even if what you wanted was the same chip on the wafer. The mask shapes would have to be different. Same for high-NA and hyper-NA for that matter. In high-NA, you have the stitching thing, and the black border effect or flare effects have to be taken into account differently. That will also create a situation where in the Y dimension, the shapes that you want on the mask would have to be different. More and more, it's getting closer and closer to having the full reticle being different shapes every time. In offline vertices-based, polygon-based correction, the conventional MPC, the computing time is counting on, especially for 193i and before, that chips are repeated. So you compute OPC or IoT and you compute MPC once, and then you step on repeat. You cannot do that with EUV and high-NA, but it doesn't matter for PLDC, because PLDC is processing the computing as the mask is being written. So it's processing all of the shapes on the full reticle, custom per location, custom for whatever is happening in that particular spot. Anyway, it's doing that no matter what the mask is. So if the shapes are different everywhere, that's perfectly okay. It makes no difference in runtime. And it makes no difference in accuracy. Zero turnaround time. What that means is there is no time spent to do the MPC task. As I mentioned, PLDC is happening, the computing is happening while the mask is being written. It's being done in parallel. Because of that, there is no pre-processing of any kind. There is no post-processing of any kind. The machine rasterizes the shapes that come in. That has to happen anyway, because it's going to be written with multi-beam pixels, right? PLDC works with those rasterized pixels and processes in the pixel domain. It works just the same as how this screen that you're looking at is being drawn. It might have some video processing to enhance some edges. Like, if you do PowerPoint, you can get sharpened edges, right? That's improving the edges. That's exactly what this one is, contrast improvement, right? You get the edge dose up. That's what sharpened edges is. That kind of processing, all of those kinds of processing in video or image processing and in PLDC works in the pixel domain. It's not working in the polygon vertex-driven domain. And because of that, the runtime to compute these things is constant. It scales by the number of pixels, regardless of the shape or vertex count. Tekscend and Micron, Tekscend in Bacchus of 2024, and Micron in SPIE Advanced Lithography and Patterning Conference in 2025, have done papers, published papers. Both papers are excellent. Most important, the takeaway from these two papers is that PLDC works. Now, the Tekscend paper specifically talked about uniformity. Uniformity enhancement is not something conventional, traditional MPC capabilities do anything about. They correct for linearity, but they do not improve LCDU. This capability, PLDC, in no additional runtime, no additional turnaround time, also enhances edges. It improves the edge dose, it improves the dose margin, and therefore, particularly in low density areas and high density areas, you have noticeable differences in how much LCDU improvement you can get. The Micron paper talked about the linearity improvement. And these are typical test patterns. So these are Manhattan patterns, right? And you can see how what they compared with offline vertex-based and MPC vendors versus PLDC. What you want to see is a mean to target, MTT is mean to target, and of 0 across the board. So, straight line would be great. PLDC isn't quite there, right? But it's much better than others. And it's way, way better than not doing anything. And all of that in 0 turnaround time. And so these are for Manhattan test pictures, test patterns. It's also important that when you have the correction, when you have the linearity correction, that linearity correction has 2 different computing kernels. One is a dose-based one. That's the classic one that most people think of. And the other is a variable edge-based one. Because the kernels, the formulations, the physics is different, you cannot fake one with the other. You have to have 2 different computing kernels to be able to do this correction. And the picture on the right is demonstrating that. Yellow, red, and blue are different densities, right? And the left side is the smaller shape, the right side is bigger shapes, and the linearity drop off, as you see, is pretty severe if you don't do any correction, and that's why you need linearity correction, right? If you only do dose-based correction, though, you can only get some progress, right? You also have a constant offset, which you can correct with a constant offset, right? But when you do variable bias correction together with dose-based correction, you get a pretty flat line. Okay, it's not 0 across the whole thing, right? But it's a pretty flat line. And it's way better than not doing variable bias, and it's way better than not doing anything. And all that works in Manhattan just as well as diagonal curvilinear patterns, right? No changes. Exactly the same pixel-based manipulation because of the nature of how pixel-based computing works. It works for curvilinear shapes too. And the Micron paper showed the sine wave pattern results. And sine waves have a similar thing to that, the circular thing that I showed earlier, right? It's not quite a sharp edge, but depending on the amplitude and the frequency, you will end up with sine patterns that have unmanufacturable tips. But it's still an interesting study, right? To see how well the corrections behave and how far it can get. there's some improvements that are being made, and they'll be demonstrated at PMJ pretty shortly. But all of this is in zero turnaround time, and there's no pre-processing of data, right? And it works because it's both dose-based and variable bias correction. All of that in zero turnaround time. I just want to be very clear that it's not like zero turnaround time for one thing, and if you add another capability, it now becomes not zero TAT. You know, like that might be intuitive, but that's not how this thing is designed. PLDC is designed to be zero turnaround time in all of these capabilities. You get all of the benefits in zero turnaround time. There'll be further discussion on this, and additional progress will be demonstrated by Paris Spinelli from Micron at the very last session in PMJ. And then, following that very last session, there will be a special eBeam initiative event. We're calling it the finale. And Paris will talk some more about other details of PLDC. And we will be enjoying Paris's talk extra by having whiskey and sake. These will be very good Japanese whiskey and Japanese sake. So please enjoy. And it's, let's see, April 18th in Yokohama, as always. It will be a great time to visit Japan. And if you haven't planned it already, please, somehow get the budget to go. And if you are planning to go, be sure to stay for the Friday afternoon session. Okay, thank you very much.